You're standing at the entrance to a corridor under Reactor 4 that no human has stood in for more than a few minutes since 1986, and even then, only in an emergency. A dim flashlight beam, concrete dust on the floor, and at the end of the corridor, spilling out of a broken pipe like something that was poured, not built. A mass of gray-brown material, wrinkled at the surface, roughly 2 meters wide, part of an estimated 100-ton pool of solidified material beneath the reactor. Whatever this is, it isn't part of the reactor design. Nobody put it there. It made itself. By the end of this, you'll understand why this object, not the explosion, not the fire, not the reactor itself, is the actual reason parts of Chernobyl are still off limits for the rest of your lifetime, and why the men who first found it started dying before they finished looking at it. April 26, 1986. Reactor 4 of the Chernobyl nuclear power plant, in what was then Soviet Ukraine, is running a routine safety test, the kind that had been performed before, the kind that wasn't supposed to be dangerous. A power surge during the test spikes the reactor output to roughly 100 times its rated capacity in seconds. 2 explosions tear through the reactor building. The graphite core catches fire and burns for 9 days, and for those 9 days, radioactive material pours directly into the atmosphere. The explosion itself killed 2 people that night. The fire, the smoke, the fallout. That story has been told 1,000 times. What hasn't been told as often is what happened underneath the reactor, where nobody could see, in the weeks and months after the fire finally went out. It took until December 1986, 8 months, for anyone to work up the courage and the equipment to go looking under the ruined reactor. A remote camera, pushed down a corridor in the reactor's basement level, sent back an image that didn't match anything in the plant's blueprints. The photograph came back grainy, streaked, almost corrupted looking. And that wasn't a bad camera. That was gamma radiation, so intense it was directly fogging the film in the camera, the same way light would if you opened the back of it in a bright room. The distortion in the photo wasn't damage to the object. It was radiation passing through solid film like it wasn't there. Scientists nicknamed what they found the elephant's foot for its wrinkled, folded shape, layered like something that had run down the wall and puddled on the floor. Here's what it is, and it isn't radiation given form. That's not physically what's happening. It's a material called corium, nuclear fuel, melted at temperatures over 2,000 degrees Celsius, mixed with everything the melting fuel touched on its way down: sand, concrete, steel, the reactor's own structural material. All of it flowed together, cooled, and solidified into a single glass-like mass. Picture wax dripping down the side of a candle, except the wax is molten nuclear fuel, and the candle is a nuclear reactor. It's roughly 10% uranium by mass. The rest is that mixture of melted building material. It's not a substance anyone designed or has ever made on purpose, before or since. The only known way to create corium is to melt down a nuclear reactor. You've probably heard the claim that standing next to the elephant's foot for 2 minutes would kill you. Here's where that number actually comes from, and why it's not the whole story. When it was first measured, in the weeks after discovery, radiation near the elephant's foot was estimated at roughly 8 to 10,000 roentgens per hour, a figure so extreme that a lethal dose really would arrive in about 3 minutes at close range. That's the number that made it into most articles, and it's genuinely accurate for 1986. By 1989, 3 years later, direct measurements found radiation had already dropped to roughly 1,100 roentgens per hour, still enormously dangerous, but nowhere near the number being repeated online today as if nothing had changed. And the decay kept going. By 2000, around 700 roentgens per hour. By 2016, about 100, enough to deliver a lethal dose in roughly 5 hours, near certain death within 8. And here's the part most retellings skip: that 2016 reading is the last confirmed measurement anyone has taken. Nobody has gotten close enough since to update it. The number you'll hear quoted as current is 9 years old, at minimum. The scientists who studied the elephant's foot directly worked in the only way that was survivable: seconds at a time, sprinting in, taking a reading, sprinting back out. A drilling attempt failed, and when a soldier tried to chip off a sample with an axe, he was overexposed for his effort. The sample that finally worked in 1988 came from firing a rifle at the mass from a safe distance and collecting whatever fragments broke loose. One inspector, Artur Korneyev, spent years documenting the site up close, including the famous photograph of himself standing near the mass in 1996. He later developed cataracts and other radiation-linked health problems, the kind of cost that shows up years afterward, not in the room at the time. It wasn't only humans who struggled to get close. Engineers tried sending a remote-controlled drilling rig into the corridor to bore into the mass for a sample. It got physically stuck on a 12-centimeter pipe obstruction and had to be manually freed, twice, before it broke down entirely. A modified reconnaissance robot, nicknamed Microbe, was sent in next just to look, but it couldn't drill the surface either. That's the actual reason the final sample was taken the way it was: a rifle, fired at the mass from a safe distance, collecting whatever fragments broke loose. The robots didn't fail somewhere else in the plant. They failed right here, in this corridor on this object. Here's something recent research has revised about this thing. For years, the popular explanation for why the elephant's foot is crumbling was just radiation breaks things down. The more precise mechanism, understood through more recent study. Alpha decay inside the corium is creating microscopic, nanoscale pores throughout the material, tiny structural voids that weaken it from the inside, which is what's actually driving it to crumble into dust over time, not radiation exposure in some general sense. There's also a popular myth worth correcting here. The term Chernobylite, popularized by a video game, gets used as if it describes the whole mass. It doesn't. It refers to one specific, narrow crystal form found within the corium, not the object as a whole. And the site itself is still an open story. The massive, new, safe confinement structure built to seal the reactor and everything underneath it, including the elephant's foot, was struck by a drone in February 2025. The IAEA confirmed in December 2025 that the structure lost its primary safety functions, including its confinement capability, with a breach found in its inner membrane, though radiation outside the site has stayed stable, and the load-bearing structure is undamaged so far. By 1998, the outer layers of the elephant's foot were already turning to dust. By 2021, its consistency was described as similar to sand. That crumbling introduces a hazard the original solid mass didn't have in the same way. Inhalation risk, not just proximity risk. Fine, radioactive dust that can travel further than the mass itself ever could. This isn't a story that ended in 1986, or even in 2016 when the last measurement was taken. It's still an active site, still being watched, still slowly falling apart in ways engineers are still tracking today, 40 years later. Sealed under a structure the size of a football stadium, monitored but not solved. Go back to that corridor, the flashlight beam, the wrinkled gray-brown mass at the end of the hall. It's still there right now, still radioactive enough to kill with sustained exposure, still quietly crumbling into dust 1 gram at a time. Nobody has removed it. Nobody currently plans to. The question nobody's fully answered yet is the one that actually matters. Not what happened in 1986, But what happens to the thing sitting under that reactor 100 years from now, when concrete and steel don't last forever, and radioactive material can outlast both? This channel finds the thing nobody else is looking at closely enough every single day. Subscribe so you don't miss the next one.